body. See ya. And stick around for the overall. Got a headliner in.
You know, so you're going to build an engine. What are you going to build it out of?
Mm-hmm.
You know?
Mm-hmm.
I don't know. That's just a thought I had.
Accumulated a few parts, give you some ideas.
Yeah. You know, these are some of the choices you have between a welded stroker and a forged stroker. And,
yeah. Well, why don't I get the liquid wrench out of the way here and just go ahead and
okay.
Let's start at the heart of the engine. Let me get this out of here.
But we're done with that.
We're done with that. And start at the heart of the engine, the crankshaft.
The heart of the engine is one of these three pieces here. We could actually start with showing even a stock 69-stroke crank that comes in the machine, but
most people have seen that.
Yeah, they've all seen that, and they've all got one. You know, if they're at this point, they don't need to see it. But both of these crankshafts are a welded stroker. You know, or you can even get this particular crank here is a 69-stroke. It's just got welded on counterweights. Okay. This crankshaft here is a welded on counterweight with a welded journal to extend the length of the stroke. It's offset ground after it's welded. Both cranks, excellent, you know, for what you're going to do with them.
And what's this beauty?
This is a new forging. This is a forging that's come from Bug Pack, I think. And it's a 82 millimeter stroke. And I think this one is a Porsche journal. This is one of the first ones we've seen like this. We haven't seen any in service yet, but it's a really nice looking crankshaft. And it gives you a lot of strength to build an engine on, I believe. You know, there's a couple new forgings coming out now that are, you know,
but a crankshaft like this, I believe here in 1983 that a crankshaft like this runs around $500.
Somewhere in that neighborhood, yeah.
Five and up.
Yeah, and up. And a crank like this, a welded crank,
goes anywhere. A welded stroker starts anywhere from 150 on up to, you could pay $375, $400 for
yeah.
one.
And they're both forged cranks.
They started out as a forging. This has had the journals welded to relocate them to increase the stroke. Okay.
So this is not a bad way to go then. If
oh no, this is the way we went for many years. Technology and engineering has produced this. You know, we've dealt with the Okrasas before. Okrasa always made a new forging in the form of a crank, anything from a 69 to an 84 millimeter. And they were very good crankshafts. They still are. This just happens to be made by somebody else now and can be bought for a lot less money.
An Okrasa crank on the average starts at about $800.
Yeah, here in 1983.
Right.
Yeah.
This particular crank can be bought probably in the $500 range, and it will do everything that anybody wants it to. You know, there's going to be crankshaft failures. I don't care what kind you get. You know, depending what you do to it and how you take care of it. You know, connecting rod. You can start out with Old Faithful here. This is the one that Volkswagen came up with. And I say anything under 150 horsepower, this rod is more than adequate. You know, I doubt very many people will argue with me on that. The next best thing after that, there's other things, don't get me wrong, but these are the things that I recommend, you know, is a Carrillo rod. It's in my opinion, one of the strongest rods. You can buy a titanium rod, but I don't even have one because I can't afford it. You know, a whole set of Carrillo rods today would sell for about $600, $650, and a set of titanium rods for a little over $1,000. You know, so there's quite a margin there that has to be dealt with strictly in the pocketbook, because this rod here is going to do everything the titanium rod will do. You know, this rod here, somewhat uncommon to the air-cooled Volkswagen people.
It's a water-cooled.
It's a water-cooled rod. This is out of a Rabbit, or a Sirocco, or an Audi Fox, or I don't know. Let's see what else would come with
Dashers.
it. A Dasher would come with it.
And even
This
the
rod has got a-
Chrysler made a motor with that.
Yeah, you could buy a
Champ, I think.
Dodge Omni and
Omni.
a few other deals made by Chrysler that came with that particular engine in it. This rod is one of the strongest rods for its size around. This particular crankshaft here has had the journals ground to the same size as the standard Rabbit or Sirocco, what have you, water-cooled engine. Even an Audi 5-cylinder 5000 engine has this same rod in it. They've ground the journal smaller and offset it off of a 69-stroke or standard Volkswagen journal. This crankshaft ended up being, without any welding on the journal, a 78-millimeter stroke. Somewhat economical in a sense that you can get a long-stroke motor with a readily available rod, and it can be done. We've done quite a few of them. You know, the hardest thing is to find a set of these rods.
Yeah, and as of today, I understand that these are available only in sets.
Only in sets.
From the dealer.
You
and,
also-
and they're quite expensive,
Right,
too.
and you also have to reverse the bolt.
The bolt has to be reversed and a nut put on it.
Good point.
Yeah.
But
Yeah.
you can take this rod, take this 82-millimeter stroke crankshaft, do the same thing to it as we did to this 69-stroke, and get up to an 88-millimeter stroke
88.
By offset grinding.
by offset grinding that crank. So you can achieve something with a rod that's available, reasonable in price, and is strong. I think it's a good way to go, especially if somebody wants a real torquey street engine, or even an off-road engine. We've seen quite a few of them in off-road engines now.
Very beefy little rod.
Yeah, it's a very strong rod. After you get done with the connecting rod, you know, all these choices that we're talking about here are things that you should think about before you decide what kind of an engine you're going to build. Don't get halfway started and then just, you know, have a set of Volkswagen rods and then decide you want to buy a set of Carrillos, you know, or you want to go into something else. You know, plan this thing so that you don't end up with a whole bunch of leftover parts that you didn't use. You know, get advice, talk to people, and you'll find that in any case, the choice you make in the beginning, if you follow through with it, will save you money. You know, you won't be doing things twice and 3 times. You've got a crank now, if you've made that decision. You've picked the connecting rod. You know, we kind of overlooked it here. The case you have, if you've got a case that's, let's say you've got a 69 Volkswagen and the case is good. There's no cracks in it, you've inspected it, and you've had it checked, and it's clean, then there's no reason not to use that case. But if you have to buy another case, and you can't find a good used one that you know is good, then the next choice you have is to buy a new case. And today, this is the case you're going to generally buy. You can buy this case right now for, on the average,
About $325 to $375.
yeah, under $400. This particular case, if you see back here, Volkswagen had a tremendous tendency to crack right back here behind number 3.
Yeah, if the camera will come in here and take a look at this built-up thing, and you can compare it to your
Well,
other cases.
Volkswagen did us one better, and they made the casting. This is a die-cast case. It's magnesium, and they basically filled this whole section in here, made this area much beefier, so that where the spigot that the cylinder seats in, right here, has got some backing. behind it, so that when you bore it for larger cylinders, it's not going to crack. You know, there was other reasons that caused it to crack, and they also solved that problem too. The case is just superior to anything for the air-cooled engine short of a new aluminum case. A few people now are coming out with their own castings, you know, with an aluminum case to replace this case. The cost of them, I can't tell you what it'll be. You know, I'm sure it'll take more than a couple hours overtime to pick one up. This case here, in my opinion, for anything you're going to do is more than adequate.
If you're going to use your old case over again, or you're going to find a good used case, you better know how to check it for cracks, where to look for cracks, and you better know how to check it for warpage. Make sure the case hasn't been overheated and warped, and that it's not cracked.
After you've decided on a case, you've decided on your connecting rods, you've decided on the crank, you're going to want to choose a piston and cylinder suitable for what you're going to do. There's good piston and cylinders from everything from 85.5 millimeter all the way up to, I don't recommend going bigger than 90 millimeter. You know, you can buy
90.5.
90.5s by Siemens. NPR makes a 90 millimeter piston and cylinder. The external dimensions of this cylinder on the OD is the same as a 92 on both ends. In other words, you could have a case and cylinder heads bored for 92s, and this will fit your case and your heads. But the inside dimension is 90 millimeter. The cylinder is much thicker, much more stable when it reaches operating temperature. It stays round. It doesn't draw itself square through the stud pattern, and you have basically a square cylinder and a round piston and a round ring in it. You know, this is what happens with 92s. There are other larger piston and cylinders available for these engines. The piston is a die cast for the 90 millimeter. It's a die cast piston. It's made by NPR. Probably for a die cast piston, it's one of the best you can buy. They come in a stroke dimension for a 69 stroke and an 82 stroke. Think about this before you build an engine. If you're going to build a 78 millimeter stroke or an 82 millimeter stroke, buy an 82 millimeter stroke piston. Okay?
That would be an NPR-B.
Right. NPR-B. You can also buy them in, I'm not sure if Siemens got them yet, in their 88s and their 90.5s in a different stroke length.
No, they don't. No.
Rumor had it they were supposed to,
Yeah,
but
well,
I haven't seen them yet.
They
Well,
may
we'll get
have
in, when we get to the Siemens, we'll
in
get
the
into
future,
that.
yeah.
They do have them in the 90.5s, but not the thick wall 88s.
Yeah, anyway, what it enables you to set the deck on the engine without using a spacer. And this is, I think, a tremendous advantage if you can do it. Okay? I still say that the NPR is one of the best die-cast pistons you can buy. Next step here is, in my opinion, the best for any use. This particular is a SEMA 88 millimeter piston and cylinder. There's a piston and a cylinder. The outside dimension of this is the same as a 90.5. Same reason as that. The cylinder wall is thicker. It stays round and retains its cylinder seal. The piston can stay sealed up in that cylinder at operating temperature and for a much greater period of time than anything else.
Mm-hmm.
The piston itself is forged. It's a forging. It's a much lighter piston. If you were to hold this piston, this feels like a brick compared to this. Depending on what you're doing with the engine, you know, can determine what you want to run with piston weight. Back to this. This has got a 2 millimeter ring, top, first and second ring on it. They're 2 millimeter faces. This has got a 1.5 millimeters each. 1.5 millimeters is a thinner ring. Higher RPM engines like thinner rings.
Mm-hmm.
You know, there's no way around it. This particular piston comes now with a thicker crown. In other words, the thickness of the top of the piston is greater than any of the other pistons you can buy. And if you get into having to notch the piston, this is something you want to take into consideration. Don't run a piston that when you put a notch in it, you're going to start cutting into the strength of the top of the piston. Like I said before, it's a forged piston. It can maintain more temperature, more combustion chamber temperature, and withstand more pressure than a cast piston can.
Yeah, now this SEMA is made in Brazil. The NPR is made in Japan, of course. And the company that makes this in Brazil is a very, very well-known and old-line German company called Mali or Mal, however you would like to pronounce it. And the other one, I believe, the COFAP, which is the Brazilian piston. I don't think you'll find it in the big bores so much, but that's made, the Kolbenschmidt.
Kolbenschmidt, right.
Is a German company. So these are made in Brazil. They've been coming out of Brazil for years now.
That's the only place this piston ever came from was Brazil.
It's beautiful.
It's a beautiful piston.
Also on the SEMA, as of very closely to the time this tape was made, SEMA now makes their 90.5 with the outer bore of 92. So that's a thick wall. The only difference in the 92 and the 90.5 compared to the 88 is on the 90.5 it has a 2 millimeter ring, like the 90, and it's not.
I don't recommend a 2 millimeter wide ring
On
for
an
a
all-
high RPM. A motor that's going to run over 7,000 RPM.
Street motor, they're fine.
It can't maintain cylinder wall pressure. It gets air between it and it loses its seal. And then you end up with crankcase pressure after about 7,500. You know, it's just not as efficient a combination. You mentioned Mala. This particular piston here, we're just going to whet your appetites out there. Any of you that buy this tape that understand anything about Volkswagens, you'll have to go take a cold shower after you see this. This is the biral cylinder, as we know it. It's a cast iron liner with an aluminum jacketed fin. Now the two are cast together. You won't find a better cylinder made anywhere, in my opinion, in the world than this here for a Volkswagen. It's very light, very, very strong, and next to impossible to find anymore. They stopped making them, I would say, about maybe 1975, maybe 1974. I don't remember that well. The piston was a forging. It was made by Mala. This guy probably forgot more about making pistons than anybody in the United States knows. The ring configuration, it had a Dykes ring on the top. I won't go into what a Dykes ring is if you don't know. I'd just confuse you anyway. A 1.5 millimeter second groove, a conventional oil ring,
Slipper skirt
and a
design.
slipper skirt design. Now the thing about the slipper skirt design,
As
you
compared to a
can
full
compare to a full skirt.
Camera can come in and see this here, perhaps.
Full skirts all the way around it.
Full skirt.
Slipper skirts just on the thrust surfaces of the piston.
It reduced weight, and it also reduced the friction surface the piston could apply on the cylinder. And the structure of the piston, if you see these struts that ran across it here, kept the piston much more stable, and it maintained its clearance throughout all temperatures. Cold, it would have, let's say it had 2,000 piston cylinder wall clearance, and at operating temperature it had 2. That's something that, this piston is the next thing to this as far as maintaining that. But you get into some of your other pistons and that, it just isn't there, you know? And that's why this piston, you look real hard and real deep at anybody that's going real fast today, and they've still got a set of these somewhere, you know?
As far as in drag racing.
Yeah, in drag racing.
But these are pretty hard to find.
Yeah, they're next to impossible to find.
A set like that on the market today, brand new set, are going for $700 for 4 pistons and cylinders.
And I'd pay it tomorrow if somebody come in and told me they had them. Okay, now we've talked a little bit about our piston and cylinder choices we have. These are all choices you have to make yourself, and your pocketbook kind of has to make this choice also, you know. But if you stay with any one of these, or this, the 88 or the 90 millimeter, for a street engine, you know, I don't care how high performance it's going to get. Both these pistons and cylinders are going to give you the best possible combination for the street. If you went to the 90.5 rather than the 90, that's fine. You know, you're not going to gain or lose that much, you know. Ultimately, I say the 88 on the 90.5 external dimension cylinder is the best you could get.
It's the thickest, right?
It's the thickest cylinder, the forged piston, the best ring configuration, the lightest piston. It has more things in its favor than anything. So that'd be my first choice, okay? Now we get down into what makes this whole thing work. And you can bolt all this junk together in it, just a compressor, you know, but everything has to work off the heart of this, and that's the cam. Cam choice is something that we could make a whole tape alone just on cams.
Spend hours and hours.
And in my opinion, I have cams I like, and 90% of my feelings on cam is what I've run and how I've learned to make them work. Norris makes good cams.
Cam Dynamics.
Cam Dynamics makes good cams. There's a lot of good cams on the market. Engel, I personally have a preference to Engel, but that's because I've used Engel more than any other cam. And I've also been able to get as much or more horsepower out of any engine I ever built with an Engel cam. You know, I'm not saying you can't do the same thing with a Sig Urson or a Norris or an Iskandarian or anything else. But everything has to be made to work together, and we've always used an Engel, and I'll continue to use an Engel cam. But I'm not saying anything bad about anybody else's cam. I want to stress, don't over cam your engine, because a 110 Engel cam on your Zenith equipped 1600 worked good, that you can keep everything the same and go put in a K8, which is a lot more cam with a lot more duration, and expect it to work. You know, the cam is great, but you've just got everything else wrong around it. If you have a cam that doesn't have over 290 degrees duration and 450 thousandths lift, then there's a whole array of valve train that you would change automatically by not having a killer cam. If you had a cam that had 500 thousandths lift and 300 degrees duration, you automatically put a dual spring on it and a good chromoly retainer, and you might give some consideration to what you're going to do with a lifter. You know, all these things have a bearing on what you choose to do. But don't think you can outguess them, you know, by putting the biggest thing in the world in it, because you're just going to have something that doesn't work at all.
Okay.
You've pretty much decided what cam you're going to use. There's an array of lifters you can choose. You can go down and buy a genuine Volkswagen lifter over the counter at the Volkswagen dealer, which is, there's nothing wrong with it. It's probably one of the best ones you can get. We've had a tremendous amount of success with the Wiseman one-piece lifter. It's not a pretty lifter. It looks like that. It's black. This is a one-piece lifter I've got in my hand here that's been modified. It's been made lighter, and the diameter of the contact surface of the nail head of the lifter is smaller.
Is there any particular lifter you should look out for that you don't want to use?
There are some lifters. I've seen them. They've got a marking on them there because they say POV, P-O-V, I think.
Is that a cast or a
Is it
cut?
POV? It's a cast lifter, but I haven't seen any of them really, you know, break any records. The experience we've had with this lifter, the Eaton lifter, which is, I think that's what this was originally, the Eaton lifter, a genuine Volkswagen lifter. If you buy, let's say you buy an Engel cam and you buy a set of their lifters, you're going to buy an Eaton lifter. Okay. In any case, never use your old lifters over again. Don't use a reground lifter. Always use a new lifter. And if you're in doubt as to what you're going to get for a lifter, either buy a genuine Volkswagen lifter, a Wiseman lifter, which is a German lifter, or the Eaton lifter. The Eaton lifter is almost identical to the Volkswagen lifter.
The Wiseman lifter comes in a familiar brown box.
Yeah, very common. Okay. Depending on the cam you use, this particular spring I've got here on my hand, this is a dual spring. You can, anything over, I say 290 degrees duration, you should, I can't get that off of there. You should put a dual spring on. It just keeps the valve train oh, I'm sorry, Gary. I just stabbed him. I got it. Anyway.
Oh, broke it.
The dual spring,
Cracked.
after a certain point in lift and duration, keeps the whole mechanism tracking the lobe of the cam. As it comes out over the lobe, it wants to come back. The spring wants to push it back. If you don't have enough spring at the RPM, or high RPM, it wants to stay out there, and it causes, what's very common to everybody as valve float. You don't want that. So after a certain point, your cam grinder will recommend, after a certain point, what spring what you should use for a spring, a single or a dual. I personally, after 290 degrees duration and 450 thousandths lift and above, I say a dual spring is a must. You can get into, in a real high performance application, this particular retainer is titanium.
Titanium retainers.
They're very expensive, but it eliminates a tremendous amount of valve weight.
It didn't crack.
No, it didn't break. I don't think it will. The titanium retainer, a set of these retainers are about $22, and a set of these are about $60. But they're stronger and lighter, and weight is a factor we want to try to eliminate in a real high performance engine.
Is there ever a danger of, let's say someone doesn't build a particularly large engine, is there ever a danger of putting on too heavy springs for the particular application?
I would never use a dual spring on a stock exhaust valve, especially if you intended it to be used every day, day in, day out. The stock exhaust valve.
No matter the cam or the stroke?
Well, anybody that, I wouldn't build an engine with a stock exhaust valve that was going to be a high performance engine anyway. We have people that come in and they want to put an Engel 130 cam with stock heads. So right away we try to deter them. There's no reason to mix match all these pieces. So you try to back them up a little bit, put them into a 110 rather than a 130. But that's just the thing I was saying earlier. Everybody wants to over-cam it. They've got a set of 40 Weber carburetors, a 1600 with a 110, and then they think, well, I'll just put a 130 in it, and I'm going to go beat all my buddies on the street. Well, this won't happen. All he's going to do is break the exhaust valves off, beat the keeper grooves up, and probably suck the retainers right through. So there's a time and place for everything whenever you're building the thing, building the motor. The rocker arms, you have a lot of choices in rocker arms, and depending on the cam you use will determine what you're going to use for a rocker arm. In the particular case of the cam grinder or the design of the cam you buy will determine the rocker arm right off the bat. In, I'd say 70% of all cases, you'll use your own rocker arms, your stock rocker arms. This particular case, here's a set of, these are stock 1.1-to-1 rocker arms right off of a 1600 Volkswagen. More than adequate in strength for any cam designed to use a standard rocker arm. You may change the adjusting screw depending on the valve you use, but the rocker arm is more than adequate. You also may change the shaft. You might put a hardened shaft and a spacer kit and lock nuts such as these here, and you'll have yourself as strong a valve train or rocker arm system that you can get. That depends on whether you choose a cam that uses a stock rocker arm. In the case that you don't, let's say you buy an Engel K8 or you buy a Sig Urson I'm not familiar with their grind numbers, but a Sig-Urson cam that required a ratio rocker, a higher ratio rocker, to maintain the lift they design into the cam, you'd buy, or you can get
the Sig-Ursons you're talking about.
the Sig-Urson rocker arms. These rocker arms change the ratio that the valve opens against what the lobe of the cam makes it do. These rocker arms here, if you bolt them on a stock cam, will increase the lift, but not the duration. Very common. These have been around for a long time. You know, they're in a very low performance application, they're great. If you're going to put them on a cam that you're going to try to get over 500 thousandths lift out of, then they need some modification. You know, they're not adequate as they are, as they're sold. You can try it, but I can guarantee you'll be bringing them to somebody to put bushings in them, or you'll be replacing them with something else later. This here is an old standby here. This is another item that's next to impossible to find. This is a empty 1.4 to 1 ratio. By the way, the ones I showed you here that were Sig-Urson were 1.5 to 1 ratio. And this here is an old empty, even says empty on it, look at that. 1.4 to 1 ratio, and they've been around for many, many years. In fact, they're next to impossible to find now.
You might want to.
This particular rocker arm here is a Gene Bird rocker arm, new one. And it's a 1.5, let's see, what were the ratios that he advertised?
1.53.
1.53 ratio and a 1.45. And in both cases, these ratios were established off of a stock cam. So after the stock cam, the ratio starts multiplying itself. And under no circumstances, and I'll recommend it right now, and if you're listening, take heed, don't buy the 1.53s. For anything other than a stock cam. You'll end up with more lift than your valve springs or your cylinder head or anything can accommodate. The 1.45 is fine. It's perfect. But the 1.53s are what happened or why it ended up that way. I've seen it, I've had them, and they will not accommodate like an FK89 angle cam. There's not enough room to open the valve. It gets so dramatic. You know, it gets so, the lift just starts multiplying to the point where you can't. The Sig-Urson rocker on an FK89 cam will open at approximately 580 thousandths, and that's a 1.5 to 1 ratio. The 1.53 ratio, as advertised, opens that cam almost 700 thousandths. There's no way that a Volkswagen head will accommodate that much lift. The strongest rocker arm on the table, I will say, is probably the Berg. Then I would say the Empy or the Autocraft, then the Urson, then the stock's probably stronger than any of them.
But for its application.
For its application is limited. Okay.
Yeah.
Cylinder heads. This is the point everybody wants to know about. It's probably where you'll put the most amount of money in your engine, you know, aside from the pieces that rotate and hold it together on the bottom. There's so many choices of cylinder heads around, it's not funny. There are more people making cylinder heads now than ever.
Okay, yeah, we'll hold this up and then you can show it on the camera a little bit. Let me get out of the way here so that you can take the center of the table here.
Okay. When you start to build your engine, if you've given thought to using anything we've talked about here so far, you're going to want to at least install big valves and port cylinder heads and reshape and redesign the combustion chamber for better combustion, better flame travel, and, you know, change compression ratio.
Move this out of the way so that you can Just move it over here.
Okay.
That'll be fine.
In this particular case here, this cylinder head is a highly modified Volkswagen head. Started out as a Volkswagen head, probably made about, or the same design since 1967 on the Type 3s. It's a dual port head. It's been extensively welded up here, through the center here. It's had aluminum silicon bronze valve seats installed in it. This cylinder head here on a 1800cc engine will produce over 200 horsepower. The same head on the same size engine with a different cam will produce less horsepower, or with a smaller cam and less compression. Okay? There's a couple things that determine the horsepower an engine can produce, and that's the compression ratio and the carburation and the cam you choose. You could take the same port design and change those other three factors and have a whole different engine. So when you're building your engine, take into consideration what you're going to do with it and where you're going to use it when you decide on those three factors: compression ratio, cam choice, and carburation. Everybody wants to run a 2180 with 48 Webers and the biggest valves possible, you know, and the biggest cam possible. Doesn't always work that way. This particular head, this has got 14.5 to 1 compression on an 1800cc engine. Not quite what you'd like to drive to church on Sunday. But in a quarter-mile drag race car, it's really, you know, the minimum. You know, might even like to have a little bit more compression than that. The average street engine, I would say, should have at least a 40 millimeter intake valve and a 35 millimeter exhaust valve. And I think that the choice of valves is a good stainless valve. I try to stay with Manley valves. This is a 40 millimeter intake and a 35.5 millimeter exhaust. And depending on the engine you build, this is just about where you want to be. You can go to a 42 millimeter intake and a 35.5 millimeter exhaust, but when you go to the 42 millimeter intake, you start running into the spark plug with the valve. So you have to move the spark plug, and that can start getting even more expensive. So stay with your 40 and your 35.5 under normal situations, and if you start really wanting to squeeze it, then you can go to your larger valves. But take into consideration that you're going to have a lot more money in your cylinder head before you get through. If you really want to get exotic, you can put titanium valves in it. And this is a titanium intake and exhaust. This is a 42 millimeter intake and a 37.5 millimeter exhaust. These particular valves cost about $50 a piece. So it's not what you want to. I don't recommend them for the street. If you're going to build strictly a drag race engine and you're real serious about it, then I might give some thought to these. You know, I brought them out here more for the comparison in size more than anything else. If the camera can come in, you can see the difference in the dimension there. That's the 40 against the 42. And this is a 35.5 against the 37. So there is a noticeable difference, and a noticeable difference in performance when you compare the two. The cylinder head, I doubt very much whether a lot of people are capable of doing their own or building their own or modifying them themselves. I recommend you find somebody that does it professionally, and upon you deciding to have them do your cylinder heads, demand that you see something they've done before. Don't just walk in and take the guy's word that he can port cylinder heads and weld them and install seats and do a valve job. Everybody says they can do that. Tell them you want to see some of their finished work, you know, so that you can judge what you're paying for. You check around. There's a lot of places that are doing heads real cheap, and you're getting what you pay for. I personally think that a good set of street heads should cost anywhere from $650 to $1,000, you know, for a set of heads complete. And the difference between $650 to $1,000 depends on what size valves you choose, what size port, and what type of manifold you use. This manifold right here is a tall manifold for a 48 Weber. It's been ported and matched to this head. There's the carburetor. And for the optimum, this is what you want for the street. You know, this is the, you know, the top of the line for a street engine, for a, you know, a fast street car or all-out drag car. They're kind of a pain in the neck to live with on the street, especially when you have to put gas in it and pay for it yourself. But that's the state of the art. You know, that's the top of the line. This particular manifold is for a 40 millimeter IDF Weber or a 44 millimeter IDF Weber. It's a smaller, shorter manifold, excellent for the street. Makes a very drivable, tunable, good gas mileage, if everything else is in tune to gas mileage. Combination. The carburetor is as tunable, if not more tunable, than a 48. Not an expensive carburetor, and will deliver good performance along with good economy. We've actually seen increases in mileage over this over some stock applications, you know.
Why don't we go through the rest of the carburetors while we're on the subject?
Real quick. While we're on the subject of carburetors, there are other carburetors available. This particular carburetor is a 40 millimeter DCNF3. They also make a 42, and there are rumors there's a 44 around. I would stay away from it if possible. The 4042 is a good street carburetor, not optimum performance. You know, if you're looking to build a real stout street engine, this isn't what you're looking for. But it's a good middle of the road dual carburetor setup.
Mr. Zenith.
Mr. Zenith, this is Old Faithful here.
Yep.
I don't recommend this in a dual carburetor application, but everybody I know that races off-road somewhere along the line has got one of these back on the shelf. It's probably one of the most reliable carburetors money could buy.
It's also good for the street.
It's a very good street carburetor. It's an economical carburetor. It's a little bit expensive today. In fact, they're almost ridiculous. But if you run across one and it's in good shape and you want to run a single carburetor, don't hesitate. They're a very good, very tunable carburetor. This is something that's kind of new on the market. I shouldn't say new. I've seen it for the last 8 years or so. This is a progressive Holly Weber. There are also some progressive Webers. They vary in size. This carburetor made its debut on Pintos and Vegas, and then kind of got resurrected into the Volkswagen. But it's a very economical, yet it does give more performance than a stock carburetor. And it's because by progressive, I don't know if the camera can come in here and show this. This is your primary venturi, this is your secondary venturi. The primary opens up almost 2/3 of the way, or 3/4 of the way, and then the second venturi, or throttle valve, opens up. And that's why they call it progressive. And what it does is when you're just driving around and you're not really looking at the performance end of it, you're using just this front venturi, or this throttle valve. But when you need the added performance and you know, come down on the throttle, it opens the second one. So you get a little bit of your cake and eat it too with this carburetor. It's economical. You can take that carburetor and with the right minimum changes in the motor, let's say a 1600 or 1700 cc engine with stock heads, the smallest angle cam they make, with that carburetor and stock compression ratio, you can double the horsepower of the motor. We've done it many times. And have it last. Nothing to have that carburetor run and the motor that it's underneath or that it's on top of give the same service as a stock engine, you know, and at twice the horsepower. So
you don't have any Hollies back here.
well,
Holly Bud Spring.
they cover enough of that in that book they made, you know, how to hot rod your Volkswagen, you know.
Well, there still are a few Hollies floating around.
Oh yeah,
That's where they should go, is float around. Right?
that's where they should float in the ocean. Anyway, cylinder head wise, like I said, you've got a million choices. Carburation, there's a million choices. If you're in doubt, ask questions. Now we'll get up into a little more exotic cylinder head here. This is ARPM's Superflow head. It's being marketed by, I don't know, there's Bugpack is doing the best job with it so far. And in my opinion, it's going to be hard to beat. I have personally flowed some. If you notice back, I think we used one of these in a flow test.
Yeah, we could show a little bit of it now, too.
Right.
On the flow bench.
And you can see that it's better than your average head, especially for buying it off the shelf. The material it's made out of is excellent. The casting is, you know, hard to beat. It's there. It will bolt right on. Everything will fit it. Your rocker arms will fit it. You know, it'll bolt right onto your motor. I don't suggest putting one of these on your 1600. It's too big. You know, I would have at least a 1800 cc motor or bigger before I start using this head.
Well, they're also coming out with a...
Yes,
Yeah, they're supposed to come
They
out
told me down there that they're going to come out with a stock
with
16
a smaller
Superflow.
Superflow head that'll better serve the needs of the smaller engine.
Yeah.
You know, and I think this is what we're going to see more of in the future, and time will tell how it works. I personally haven't seen any in service on the street yet. This is a counterweighted forged crank right here that's going to start being installed in a motor that we're going to watch go together from stage one, you know, almost from the time the customer called and said, this is what I want, all right? And maybe we can convey some of the things to watch out for, the things that are going to be needed to do when you assemble a motor like this. You know, there's a lot more things to watch out for. Clearances, because the engine's going to see more RPM. We're going to want to see less clearances in some places, tighter clearances in others. The strength of the parts you use are a lot designed, you know, it comes from the fact that you want this thing to do a certain job. If it's gonna produce 150 horsepower, you can take and install a Volkswagen rod in it with not really a lot of trouble, you know, and it will give you good service. It will last, you know, a reasonable amount of time. A motor that's going to see 200 horsepower and be nothing but drag raced, I would like to see something used in the form of a Carrillo, a rod like this, and you're looking at a lot of money, but it's something that is going to reward you in the end. You know, this rod here is only good for so much. This one's good to the end.
This other rod was just a stock Volkswagen rod.
Yeah, this is a stock Volkswagen rod out of a 67 and later engine for all practical purposes.
Good rod, though. Really.
Yeah, it's a magnificent rod. It's, in my opinion, there's probably not a better rod designed for its uses, you know. And for the average guy at home that's going to build a hot rod street Volkswagen, this rod is the ultimate, you know. And we won't dwell on this rod very much, only in comparison to certain clearances, you know, and the fact that it's going to be stronger.
And in an all-out race application, the Carrillo rod gives you the peace of mind where you know it's going to be there. You know, granted, if you don't put it together right and you don't follow, you know, basic tolerances and clearance things, you're not going to have any failure out of that rod.
Something that should be said now, before we get much further into it, is that a high-performance Volkswagen engine doesn't need to be a 2180. You know, it can be a 1600, it can even be a 1500.
You mean I don't have to bore it out or stroke it?
No, it's not. You won't see the ultimate end, but it's not unheard of to see as much as 100 or more horsepower from a 1600. You know, granted, the larger you go with the motor, with respect to reliability, you're going to see more, a broader torque range, but you're going to spend more money to get it. You know, a 1600 with the right cylinder heads and the right cam and the right carburation can give you a real easy 115, 120 horsepower. You know, you can build an 1835 with 92s, which I don't really recommend. You know, 88 millimeter, 90.5, these are fine. The cylinder wall is of a design that can stay around and keep cylinder pressure and give you some kind of results, you know, over a long period of time. So I won't say a lot about it now, but
yeah, well that's usually the cheapest and easiest and quickest way to do it. That's
right.
why most people choose it.
When they're new, they're fine.
And most people go, if their first instinct is to go with, if a bigger is better, a little bit bigger is going to be even that much better. It's not true, because you lose efficiency through what you lose with the size and the cylinder wall.
Yeah.
Granted, when you put it in, you first start it up, it's going to work real good.
Yeah.
But a couple thousand miles down the road, you're going to lose a little.
And I like the smaller motor.
Yeah, the smaller motors seem to make every bit as much horsepower as the big motors, and you don't have to, in fact, maybe even a little more.
They seem to be down in up in the RPM range, I mean to say, is I've been told by Dick Nuss that they work, and I doubted them for a while. I don't doubt them anymore.
No, seeing is believing.
They, right today I'm running one of their old motors, and
that's the one that they've ran actually in their A car into the 30s and 40s,
right,
isn't it?
yeah, they, same exact motor.
Very, very competitive.
Yeah, it's a fast motor.
That's what, 1700?
1700 cc.
1700 cc's.
102 cubic inch.
In a high performance engine like this, this engine is going to be, this particular engine is going to be a 74 millimeter stroke by an 88 millimeter bore. It's going to be a all-out drag race motor. Now, there may be a few things that you're going to have to back off on a little bit if you're building an engine that's not going to be a drag race motor, but a lot of the theory will apply. A lot of the setup in the motor will be identical to if you were building a 69 stroke by 90.5 with a good set of street cylinder heads. The clearances throughout that motor will be pretty close to the same. You know, you're going to rev it up a lot more, you're going to want more side clearance on the rods, you're going to want maybe a little bit looser clearance on the bearings. You know, it's never going to last as long as a stock engine. Don't ever think it will. You know, there's no way it can. So on this particular crank here, with this Carburetor rod and a stock rod, it's evident there's only about a thousandth of an inch difference in the side clearance or the thrust clearance of the rod. In this particular case, we'd like to see the thrust clearance not less than, I'd say 7 or 8 thousandths, and not more than 17 thousandths. In this case here, the Carburetor rod comes up with a side clearance or a thrust clearance of 12 thousandths, where the stock rod, because it's not meant for quite as high performance, it drops back down into the 10 thousandths range to the clearance of the rod in here. And you don't want to have this too tight because there's no escaping for the oil, and it pressure locks itself and then it gets hot. The oil has to flow away from the bearings in order to remove the heat.
And when this crankshaft's spinning in there at 4,000 RPM or whatever, the oil that's coming out here is being spun in a huge circle, and it goes right up into the pistons and liners.
Right. It lubricates the cylinder walls, the wrist pins, even helps lubricate the cam.
Now, if you have too much clearance,
25 thousandths probably wouldn't hurt, you know, even in a stock machine. The thing it tends to, every time the explosion takes place in the cylinder, it forces that rod to one side or the other and creates noise. and it will create wear ultimately. There is good lubrication there, so it's going to take a while, but it's not going to get better. It's going to get worse, and you'll have a noise factor, you know.
So side clearances are very, very important.
It's very important in respect to too little or too much. It's got to be right. You know, that's why we're saying it should be between, in a racing application, I wouldn't like to see less than 10 thousandths. Now, you may find people that'll disagree with me there, but I found the best bearing life I found in our own racing engine that, you know, 10 to 12 and even up to 15 thousandths doesn't hurt and hasn't worn anything out yet, and that's where I'm going to keep running it.
On a new 1600 crankshaft and rod, what's the average clearance there? Is there an average?
Yeah, about 7 to 10 thousandths. You know, which is plenty adequate because the motor never sees more than about 4,500 RPM. You know, and this particular engine is going to start producing good horsepower at about 6,000 RPM and continue to produce horsepower up above 9,000 RPM. So we're dealing with, we're out of the range of the stock engine, you know, which makes it kind of hard to believe this thing will withstand those kind of, you know, pressures in RPM, but they will if they're assembled right and have the right clearances.
This is a beautiful crankshaft. It's really a nice piece of machinery to look at. Well, what are the different crankshafts that are available to you?
Well, the basis for a good engine, in my opinion, is a good forged stock Volkswagen crankshaft. There's probably not a better forging made than that crank. There's welded on counterweights. That you have a choice of cast iron cranks, which I don't recommend, especially in a high horsepower application. You know, they.
So you'd have to specifically say when you're talking about crankshafts, how is the crankshaft made? Is it cast or is it forged?
I would. A crankshaft should be forged, in my opinion, for a high horsepower application.
Well, let's back up. You're talking about an all-out race motor. If you're building definitely high horsepower, high RPM motor, a forged crank is definitely the way to go. If you're building, you want a good reliable street motor, we recommend that you go with either a forged crank if you want to put the money in it, or to a welded stroker, which becomes, it is a forged crank to start with, they weld the counterweights on. This particular crank, this is all the counterweights and everything is forged in one piece.
I think right over here we have a welded stroker there. Grab that over here and we can compare the difference.
You'll be able to see the difference.
You can see the weld line on it, and there's not a thing wrong with the comparison of these two cranks right here. Let's see if we can't get it so you can see the fact that it's welded on.
Right in here.
Yeah, right in here, right here. This whole counterweight is actually welded on, and in order to change the stroke, they actually weld the journal outwardly from the center and then regrind it back to standard, and it changes the stroke. The stroke is the distance the piston travels down and up the cylinder, and from the center line to the journal here is half the distance of the stroke.
Put it back on top of here and show them that basically in making these two cranks, all of this material here was forged onto this crank. Where if you look up here at the counterweighted crank, this whole counterweight you see sticking off here that looks like that has been welded onto it. The actual crankshaft they started with was a forged crank.
The stock Volkswagen.
It was a stock Volkswagen crank, and they welded the counterweights on it. It does stiffen and make the crank a lot more rigid for flexibility through the RPM range. And going back to, I think we should come back to picking a crank for what you want to do. We recommend in a very high horsepower, high RPM application, a forged crank is better. Your next choice would be going down to a welded stroker, which is a forged crank with just the counterweights welded on. We're not saying you can't use a cast crank, you know, which is, you know, normally just a cast iron crank or sold that way. Fairly inexpensive. They are cheaper to make. They aren't as hard. They don't have the wear tolerances or abilities in it and whatnot. They don't tend to last as long, and if you do start to use them in a higher horsepower, you're going to see a lot of problems. You can go into that a little bit with the dowel pin.
The tensile strength in a cast crank is not that of a steel crank, and the dowel pins that hold the flywheel on, if you rev that motor up to 7,500 RPM and dump the clutch, something's going to break. And it's generally going to be the flywheel coming off
Just
the
to
end.
show
We
the
could,
dowel pins. It just, we're not saying not to use it. We're not telling you.
Yeah.
We're trying to give you a basis as to what is better than the other and to pick the best application, like Dick had outlined earlier. Getting what would work best for your application.
The size of the motor has to be determined by the size of your pocketbook a lot of times, because a stock 69 stroke Volkswagen crank with welded on counterweights, costs about $150, and will actually do the same job that a forged 74 or 78 or 82 stroke crank will do in the form of reliability. It's just that the physical size of the motor, the difference right there is going to make a difference in the horsepower and the torque curve in the motor. This is something we'll talk about later when we get into what different size motors can do for you.
And I think you can also mention of having it wedge mated.
Wedge mating is a process of holding the flywheel on that
Takes
it's
it
an
one-
interference lock between the flywheel and the crank, that when the flywheel is pulled up with the gland nut to the torque it needs, it actually interferences the flywheel over the end of the crank and almost makes them become one. And if you're going to drag race your car and you got in the neighborhood of over 175 horsepower and you use slicks on the car, this is a good way to go.
Right.
It's not imperative, but it's a good, safe way to keep the crank and flywheel you've got in one piece.
Well, it's in basically saying if you're building an all-out drag race motor, wedge mating is definitely something that you should do.
We're going to go on from here and take this crank and we're going to put the rods on it and we're going to lay it in a case and show where this stroker crank interferes in the case, where it has to be clearanced. Now, some cases vary. Your case might be able to take a 74 stroke crank without clearancing, but by all means check it. We're going to show you how to check it, the places to watch for in the case. You may see that our case doesn't hit where your case does, or where your crankshaft hits in your case. Might not be exactly the same, but 9 times out of 10 it will be. So pay attention and maybe take a few notes so that when you're out in the garage and you're not looking at the tape, you can check these places. We've put these rods all on the crank, and we've put the crank in the case. Now, sometimes it's easier with them on and with them off if there has to definitely be clearancing. In this case here, we want to show where everything's going to run into each other. One of the most important things to check first, because it isn't always obvious, is that when the crank is pulled up laterally up against the thrust bearing, that there's ample clearance on the webbing of the crank.
Show us the webbing on this and
Okay, the webbing on the crank against the webbing in the case. Okay? Aftermarket cranks especially tend to be a little thicker in the webbing and they may interfere here. There's differences in cases and cranks, so it's a place to be careful. Look for a problem there. You might not have it, but check it anyway. If it's good, then go on. Okay? The next thing is the rods are going to run into the case. As the crank spins around in the case, the rods are going to come around and hit the case. One of the most obvious places is going to be at the top of the case, here, where the rod comes in. It's going to, all 4 rods are going to do it. It's going to interfere. There's going to have to be clearancing done here. The other place is down in the bottom of the case, on the opposing end of the rod, at the cap of the rod, is going to run into the webbing in the case, right through where the case savers come back in, on all 4 rods, opposing sides. Okay? The rod nut itself is going to run into the case directly in the middle of the spigot hole, top and bottom.
Yeah,
Okay.
right in here and here. Huh?
Right.
Yeah.
And all 4 cylinders.
On both sides.
Both sides, everywhere. These places have to be clearanced. When the time comes for this, take it somewhere where they have the equipment to do a Volkswagen case. Another area is the cam. Anything much over 74 stroke, 74 millimeters of stroke with a Volkswagen rod is more than likely going to interfere with the cam.
Mm-hmm.
The most common place is on the center main journal of the cam, about 3/8 of an inch in. The cam has to be turned down in its diameter, just about the diameter of the casting of the cam.
Mm-hmm.
You know, that diameter up here about 3/8 of an inch. On the thrust side, the back side of the thrust of the number 1 bearing there, or the bearing by the gear, has to be cut here. Now, this is something that just about any machine shop could do that has a lathe. You know, it's a very simple operation. There are other methods to do it. We'll show you different methods of cam clearancing, depending on the stroke and the motor.
Well, we will also show you cams that have already been
Yeah.
clearanced in the 2
Right.
spots.
It'll be a little clearer, but right now we're trying to get it understood where to look for problems. You may have a 74 stroke with a Volkswagen rod, and it might not hit it, you know, but check it. Don't leave a question unanswered. You've spent too much money on the parts you got in this motor to waste them the first time you try to start it, or not even get it started, you know.
When you check clearancing, let's say you've done all the machining and you think you have it clearanced. At this point, would you mock the engine up?
Definitely so.
Uh-huh.
Just assemble it with a little assembly lube, put the rods on it, the cam in it, the crank gear, the bearings, put that case head together, and rotate the motor through quite a few cycles.
What would you go so far as to taking the rings off the pistons and putting
Yeah.
them on the pistons in the barrel?
We'll cover that when we set depth,
Oh,
okay?
all right.
Because there is a possibility, depending on the piston you use, that you may have to clearance the piston. Below the pin boss may need clearance, and even the cylinder might need clearance if you get into some longer stroke motors, depending on the design of the piston, who made it. Okay? I think we've pretty much covered everything that the cam or the crank is going to run into, except for the lifters. Okay? Now, I'm going to take this crank out of here, and I'm going to set it aside, and we're going to show you where to look for a problem. It's going to be a real common problem. Start to assemble a motor. And even in the case of a completely stock stroke motor, if you have other than a stock camshaft, this is one thing you want to definitely check. You can do it without putting the case halves together. You can do it, you know, all you have to have is an old set of cam bearings and the cam you're going to use. Bill got us some lifters here, and easiest way to do this is just take whichever lifter you choose. In this particular case, we're going to use a Wiseman lifter. It's a German-made lifter that I'd say 9 out of 10 times will give you all the service you need.
That's a cast lifter.
It's a cast lifter, but it's we found it to be very durable, and it's lasted in a lot of engines that have 7 to 9,000 RPM range with dual springs and a lot of lift on the cam, and they give good service. Okay, what we're going to check here is when the cam is seated in its bearing again, and the lifters are in their holes, okay, and the lifter bosses, just rotate the cam around. And we've got a problem here. We can see it. The nose of the cam, or the lobe, comes around and actually interferes, you can hear it, with the face of the lifter. Okay, now what this tells us is that the lift that's in this cam, because it's not a stock cam, it's got more lift to open the valve further, it's running into the lifter. Now, if this were a stock engine, we wouldn't have this problem, but we're not building a stock engine. So, rotate it around. We know, okay, That one hits. The next one hits. You got one that doesn't hit over here. Okay. Don't ignore it. When you take this apart, you might mix up the lifters and they might not be exactly the same, and they could give you the problem again. Okay. What we'd like to have is about 30 thousandths clearance between that lifter and the lifter boss.
Yeah, when the lobe is straight
When
down.
the lobe is straight down. Okay. We have to allow for some valve float in the motor. In this particular motor, we have to allow for even more, but 30 thousandths is a good rule of thumb. Now, what we'll end up doing is the lifters have to go deeper into the case. We've got a tool that comes in and cuts this surface and re-chamfers it. And depending on how much it interferes, we cut that much out and then give it its clearance. It's very simple, and it's something that you're going to have done. When you take your case to have it clearance, or if you send it to us or to anybody else, specify you want the lifter's clearance. Okay? And they'll spot them off, chamfer them, and by no means, I don't care who did it, even if I do it. When you get it back, check it. Don't assume that anybody did it right. You know? And if it's possible, when you send the case to have this done, send your cam with it. So, and the lifters.
And
they can check it for you right then.
And the cam manufacturer won't tell you that you need clearance here.
They very rarely know it. You know, they don't see the case. You know, they've got a room full of people grinding cams. That's all they're doing. You know, they know what the cam has to do.
They make cams, they don't assemble motors.
Right.
Yeah. But that's one of the things that you really want to watch out for unless you're using a stock cam. You know? So that's pretty much it on the clearancing. We'll show a case a little later. This had all these operations done to it, and we'll show you how it was done.
Double thrusting the cam.
Okay. On a motor that's got dual valve springs and a lot of high RPM, the thrust of the cam, this surface here, this flat surface here and here, rides up against this surface of the bearing. Okay, and the standard cam box of bearings comes with only half of the one bearing for the thrust. Now, what we recommend is that you buy 2 sets of cam bearings. You know, they're not expensive.
So you have two shoulders.
You have 2 shoulders. You have a full face across that. You don't just have half of it. You would insert the other cam bearing over here. They'll stay put. There's enough pressure on the bearing not to concern yourself with the bearing spinning. Okay? There's no locking tang or anything like that like the rest of them have. But don't worry. You can, if you really feel like it, in the side that's got it, you can put a little dimple in it right up here where the pointer is, and it'll maybe give you a little peace of mind. But I wouldn't stay up night worrying about it. That you will double the life of the thrust, and when you run a heavy valve spring, a stock valve spring has in the neighborhood of 50 or 60 pounds pressure on the seat, and a dual spring has about 140 pounds pressure on the seat. And when you're running that cam around, it's trying to open that much more weight, so it applies thrust because of the bevel cut gear. You know, it's trying to drive that cam this way, okay, or this way, you know, depending if it's opening the valve or closing the valve. So these are things that'll just help keep this high performance motor alive a little longer, you know, cut down on a little noise.
Okay, we got the clearancing. We've talked about the cam. We've talked about the crankshaft. These super special rods that we have in here now. I'm going to let you take it over from here, and let me get out of the way, and you can talk about what we have set up right here.
Okay, we've clearanced this case to take the longer stroke. We've gone back and taken the rods out that we started with, only because this engine, when it's through, is going to have these Carburetor rods in it. We started out showing you the clearance that a case needs with a Volkswagen rod. You know, the average guy at home isn't going to step up and buy a set of Carburetor rods, and I don't blame him, at $600 a set. In this case right here, we'll show what the end result was on the clearancing, and you'll be able to see a little closer what we did. These were the areas, I'll hold it up like this. This area up here was the area we talked about clearancing. In the top of the case, in the spigot of the case, and in the center webbing of the case. Now this has all been taken care of in this case, and the crank rotates, the rod's clear, everything is fine up to now. Now we're going to put pistons and cylinders on it, and because it's not a 69-stroke engine, it's a 74-stroke engine, or in whichever the case may be, it might be an 82-stroke engine. The deck height of the piston in the cylinder, as I bring this around, we'll try to get up here and show it, is, well, we're going to show them how to dead stop it, so they know that if their pulley's correct or not. But deck height is the distance from the top of the piston to the top of the cylinder. You know, depending on the RPM of the motor, the type of rod in the motor, and the compression ratio in the motor, designates what this deck height should be. Under no circumstances, it shouldn't be less than 40 thousandths or 1 millimeter. You know, and you can alter this deck height by either cutting the top of the piston, and or the bottom of the cylinder, or by accommodating the base of the cylinder with a shim or a spacer. There's a number of different ways you can do it. If it's at all possible to do without a shim, I recommend it. You're just asking for a possible leak with a shim. And in this particular case, because of the design of the piston and the cylinder design and the length of the rod that we're dealing with, we probably won't have to use a shim. You know, it's going to come in pretty close. And I'm going to back up a minute here. And first of all, when you decide what the deck height is, you have to know before where top dead center is on the motor. When that journal or that rod is at the maximum length of its stroke, or top dead center. And we've got a tool here it's real easy to make. This one's a little crude even, but it does the job. Why don't we put it in on these two, Bill? Grab the other two studs.
What we have here is a flat piece of aluminum stock, and it's got a screw tapped in it.
All we're really going to do is we're going to dead stop the piston a few degrees before top dead center, rotate it backwards until it stops again, and take notice. Take notice of the difference, and split that difference, and that'll tell us what top dead center is. We did it right. This might seem to be kind of a long, drawn-out process, but when you've gone to the expense of building a motor like this or investing in the parts, and you're going to set it up yourself, there's no sense in doing it so that it's wrong, or it doesn't give you the ultimate end result that you wanted to achieve with the engine.
So what we have here is this plate around here that's holding the barrel flush against the case.
Right.
With some,
This just takes 2 spacers. You don't have to have this plate. I have this plate only because it doesn't let these spacers run down on the fins of the cylinders and break them off. You know, you spend $150 for pistons and cylinders and break the fins off of it. It's not a real good idea. Okay, now what we're going to do, we're going to crank this screw down a little bit. We're going to bring the motor up. The piston comes up and hits the screw, okay? Comes up and hits it, and on the front of our engine, we're going to look where the case half splits, and we're going to see just exactly how many degrees before top dead center that it's going to hit. Now, okay, it's hitting it right now at 8 degrees. Okay, and we're going to rotate this back all the way around the other way, and if everything's right, it's going to stop at 8 degrees again on the other side of top dead center. In this particular case, we're right on the money. So this crank, this tells us right now that the crank is in index and the pulley is correct to the crank. There's a possibility that through the manufacture of the crank or the pulley, it could be off 1 or 2 degrees, maybe even 3 or 4, but, you know, for what we're going to check, we want to make sure it's right. So we know that when we read top dead center on this pulley from here on out, it's going to be right. Okay?
So it's just a basic check you're making there.
It's a check. It's not, it doesn't have to be done, but it's a good idea. You know, if you're going to continue to build engines of this caliber, these are simple things to make. There's no reason to, get into extravagant, expensive equipment, but it's simple, makes the job a lot easier. What we're going to do right now is I'm going to come down and we're going to bring it around till it is right on top dead center. Okay. I'll buy that. That's top dead center. Now, I'm going to use a depth mic here. We'll see if it's zeroed correctly. It's good. And lay the mic or any checking device you have, bring it through the center line of the pin. Don't check it here or don't check it here. Check it right through the middle. The piston will rock in the cylinder a little bit and give you an incorrect reading. So that right through the middle, right dead in the middle of the piston, is where you want to check the deck. Okay? Or you can check it out at the edge, just to check consistency, or the fact that the pin is straight or the rod is straight. There's a couple other things you can check at the same time where it'll tell you if you find something out of whack with it. Okay, this is a depth mic. You don't ultimately have to have a depth mic to do it. You can do it with the veneer calipers and a straight edge. You know, it's not absolutely necessary. Okay, I'm going to do a couple places across the top of the piston just to see if everything's right. And so far, it hasn't moved at all. I'll turn and read the mic. About 63 thousandths. About closer to 65. Let's see. Let me check that again because I think I moved it. Six 68 thousandths deck height. So that's a lot of deck. That's more deck than we want to run in this motor. We want to run this deck at about 45 thousandths. That means the distance from the top of the piston to the top of the cylinder is going to be 45 thousandths. This is 68 thousandths, so we're going to subtract the difference between there from the bottom of the cylinder. But before we go any further,
23 thousandths.
Yeah, we're going to take 23 thousandths off the bottom of that cylinder. But before we do that, we're going to check all the other cylinders.
All four.
All four of them, just like we checked this one. At top dead center and dead stop it. Only because the journals on the crank could be out of index from the others. You don't want to go ahead and, there's nothing you can do to correct it, especially if you've got a new crank and it's possible and there's no recourse on it. But we want to make sure that we check the deck at top dead center.
And I think we should probably bring into this right now checking deck and what you want for a deck height. Dick had originally, earlier said 40 thousandths or 1 millimeter. That's fine. There are certain applications,
I think
certain
you said
type of
that.
cranks that are gonna need a little more deck. SPG rollers. Those rods stretch a little bit, the bearings and everything, they tend to need up to about
60
60 thousandths. Otherwise, the piston will hit the top, you know, the head.
We'll say right now that we're talking about a plain bearing crank right now.
Right.
You know, I'm not
And-
even
Yeah.
getting into a roller crank.
Anybody using roller cranks
Not too
anymore?
much anymore. They're awfully expensive and rather frail. You know, people are using them in off-road racers, you know, that don't see a lot of RPM or a lot of torque application. You know, I've seen a lot of failures of them that they get quite catastrophic when they break in the case.
Usually take a lot with them.
And there's not much
Cases,
left.
cams, pistons, and cylinders.
The plain bearing crank has really proved to be the most reliable, long life, you know, it's a serviceable item. You have a roller crank and you lose a rod on it, what do you do with it? You know, there's a few people on the West Coast here that can repair it, but at a tremendous cost. And once they've been repaired, they're never quite the same as they were when they're new. So we don't push it. They're not good at all for drag racing. And if you had a high-speed car, let's say you were going to drive on the freeway forever, you know, at 75 or 80 miles an hour, great, good crank. For what we're doing, it's just not working. Okey-doke.
What are we going to do next?
Well, we're going to go through and
Check all
Control that.
four.
yeah, well, we're going to check all four, and after we come up with an average, okay? Let's say we come up with a deck of a consistent 65 to 68 thousandths, okay? And we're going to take that average and correct it to an in-between, you know? We may have one cylinder that's going to have 43 thousandths, one's going to have 45, you know, maybe one's going to have 44. But that's so close that there's no reason to try to get it any closer. If you wanted to get it closer, set them all on the short side. In other words, set it all to the 43 thousandths, and you want 45. You'd have, let's say you have one cylinder is going to have 45 and the other three are going to have 43. So we cut the top of the piston 3 thousandths, and then you'd have exactly the same deck. You know, but you could start this thing up and run it and shut it off and check the deck again, and you probably have a variance of a couple thousandths from that point on.
So what is after we check all four, what would be what are we going to aim for
We're
the
gonna-
deck on this particular engine?
45 thousandths is what I
45
want on this
thousandths,
motor.
okay.
So I'm figuring the compression ratio in the head with that particular deck. That volume in the deck is used in calculating the compression ratio.
What would you say the maximum you could cut off the top of that particular piston?
That piston there, in this particular application, I wouldn't want to cut more than 5 or 6 thousandths off it, only because we need the top of that piston later on to be the thickness it is for the notch for the valve. Okay?
It's going to have a notch that's probably about 240 thousandths deep.
I see.
We need all the thickness we can get.
You know, in the case of an engine that didn't need notching on the piston at all for valve clearance, you could run a piston 120 thousandths thick. In other words, you could take 100 thousandths off the top of the average piston and not hurt it in a way. But there's better ways to accommodate deck than cutting the top of the piston a lot. I don't like to do it, you know. Okay, we're going to take this off.
Now you want to start out talking about what happens when you have a
Okay.
longer
And this-
stroke,
a longer
a
stroke.
78.4,
Yeah.
or just a 78.
78 millimeter stroke
By
and a Volkswagen rod.
Right.
This particular engine isn't the same one that we were dealing with over here. This has got a 78 stroke crank in it with a Volkswagen rod and a 90.5 piston and cylinder assembly, and the stroke dimension, or the pin to deck height dimension on the piston is still set for 69 stroke. So what does that leave us with? It leaves us with the piston sticking out of the top of the cylinder. You know, not a good way to leave the engine. Okay? What we have to do is measure how much the piston sticks out and the difference between the top of the cylinder and the top of the piston plus what we want for deck height. In this particular case, because we've got a Volkswagen rod, we're going to try to get 50 thousandths deck height in it. Where in this motor here, we were looking for 45 thousandths. We're going to try to get 50 out of this. All right, so we're going to measure from the top of this piston to the top of the cylinder. Take the depth mic again, but rather than spread the top of the cylinder like we did before, we're going to go over the edge of the piston, still through the center line of the pin. This way we don't end up dealing with this rock that's in the piston here on the pin, in the cylinder. Okay, we leave it stick over. We bring the edge of the pin and the depth mic over to the side of the piston, and we come down and we come up with a measurement. Okay.
Which is what?
Get it right. We've already achieved our top dead center like we did before.
We should have 120 thousandths roughly there, huh?
Yeah,
120 thousandths, we're going to put, we want 50 thousandths
50
deck.
thousandths deck, we put 170 thousandth spacer under it.
Makes sense.
Okay?
Mhm.
So, we're going to take this back off. We're going to slide this spacer that's under here. Let's show here, never trust what anybody tells you. If you got a means of measuring it, check your spacer. We want 170 thousandth spacer. We've got a,
That's a dial caliper there.
yeah, it's a dial veneer caliper.
Mhm.
We've got 170
That or
thousandths.
a micrometer, either one.
You know?
Mhm.
Okay. We didn't get head, so we'll slide that
On the bottom of the cylinder.
spacer on the bottom of the cylinder. We'll slide it back over here, like so.
Dick, where do you get those spacers?
A lot of different places you can get them.
A lot of aftermarket shops
You can
sell
call,
them,
you can call here and order them. We can get them usually within 2 or 3 days.
Basically,
They have to be, if you've got a custom application, we can get a spacer made to any dimension. If you're building a very basic 74 by 88 engine, and in all theory, a 74 stroke motor needs 100,000 spacer under it to achieve the, the correct deck. You can order spacers that are already designed that way, but I don't like to do it because you're dealing with a case that might be a used case and might have been decked at one time or another. Rod length varies, stroke in the cranks vary, so you never really know for sure what you're going to have. And that's why we go to the trouble to check this, to be a little more precise.
Are you going to use any kind of gasket?
No.
No gasket
No
at all?
gasket.
What
Never
kind of
use-
sealing material are you going to use?
In the case of the engine staying together for a long time, we'll use like 3M weather strip cement. We'll get a tube of it here in a minute. It's an adhesive.
Yeah, yellow
And
adhesive.
It's, yeah, there's a lot of other names for it. Yellow death, do a lot of funny things with it. But put that on each side of the spacer, or the shim, and put the thing together. When you're going to assemble it, put that on only if you're going to torque the heads on. Don't put it on the night before and then the next day torque the heads on, because it will set up a little bit and take up some deck and eventually pound out, and you'll have some loose cylinders.
And getting back to the spacers. You can have spacers made anywhere in the country of Blanchard ground. Any machine shop that does Blanchard grinding is what it's called, can make spacers like this. Because they can hold them flat and grind them. And it's a very accurate way of making them. These spacers we had made up for this motor after we had checked it.
It's kind of an oddball because it's a 78.4 millimeter stroke. Common to Okrasa and a few other crank manufacturers will come up with some oddball strokes. You get into some 76 millimeter strokes that just give you fits when you go to set deck on one of those. And, one way or other, you can accommodate the deck with the proper shim. Okay, we're gonna check the deck now. We've put the shim under it. we've got everything back together again. We're going to check the top of the piston to the top of the cylinder. All right?
Right along in here.
We're going to
So
put
it
the
doesn't
depth
rock.
mic back on it again, right to the center. We're going to crank down the old depth mic. And
Voila.
right there we got 49 thousandths. You know, I don't think they can see it on there, but it's 49 thousandths. We want 50 thousandths. I'd be satisfied with that, you know.
Great.
Okay. Go through and do the rest of your cylinders. You know, like I said before, don't trust this one that the rest are going to be right. Do all 4 of them. And one thing is if you do go into any machining of the cylinders, whatever you do, they all have to be the same. Don't let somebody say, well, you got 45 thousandths here and 50 thousandths here. We'll just cut 5 off of one of the cylinders. You'll end up with a big problem, you know. We have people come in with this thought in mind, and it doesn't work. You know, you end up with some leaky bases and leaky cylinder heads at the
Well,
same
you
time.
have to have the same height here to here on both
The
sides.
cylinders all have to be the same length. You know, so that's why if you're going to cut them all. Keep the engine uniform, you know, in its dimensions.
And make the difference between the two on the
On
top
the
of the
piston,
piston.
you know, and, you know, get your averages. And deck is important. Too little deck, you'll hit the piston on the cylinder head in high RPM. And the deck gets real small, you can even create a detonation problem. You know, the air just can't get away from that distance at the base and the top of the cylinder head, and it actually statics the air and creates enough heat that it'll detonate. It'll create enough heat in the combustion chamber. So them Germans, they were pretty clever when they, you know, come up with that figure of 1 millimeter. You know, you shouldn't have less than 1 millimeter. And depending on the application, we like to see 45 to 50 thousand.